Good afternoon, and thank you so much for joining us for the webinar, Engineering a Cleaner, Safer Energy Future. Just wanted to let you know that we welcome you so much to the webinar series by the University of Calgary scholars. Information presented is a summary of the scholars' research, in this case, Dr. Ian Gates. Please feel free to submit your questions throughout the webinar, and we'll answer as many as we possibly can. And there's some resources that will be provided, as well as slides, and a recording will follow. Also, at the end of the survey, or at the end of the webinar, you'll see a survey. So we would love and welcome your feedback. Now, it is my pleasure to introduce Dr. Ian Gates. He is a professor with the Chemical and Petroleum Engineering Department at the Schulich School of Engineering here on campus. He's also director of the Global Research Initiative in Sustainable Low Carbon Unconventional Resources, a $75 million Canada First Research Excellent Fund that's now 3 years into its 7. Ian Gates' research focus is heavy oil and oil sands recovery process design and optimization, and in his words, other stuff. So please welcome Ian Gates to today's webinar.
Well, thank you for having me. And
we have a bit of a poll here for the audience. Mm-hmm. We're going to check it out and see who's watching today. See if it's engineers, engineering students, some industry. Who do you think it will be?
I think there's a lot of folks that are just interested in the topic. So I'm going to choose that one. Choose that one. How about that?
All of them. A 25% split. Okay. Should we check it out? Alrighty. Hey, nice job. 55% are just interested in the topic.
Excellent.
Alrighty. Okay, well, without further ado, we look forward to hearing more details about what you're going to be talking about today.
Yeah, so I'm going to talk a bit about energy and energy transactions. Really kind of some thoughts on where energy is at and what's happening. Then also a bit about oil sands, and then how do we build value from oil sands? What alternatives are there to producing bitumen and heavy oil from these resources? Because they're incredibly valuable to Canada. And moving forward with environmental pressures and other things, we need to think about alternatives to straight bitumen production. Of course, bitumen production will continue, but need to think about other things, other aspects of that. But what I really want to convey here is I want to convey what we're doing at the university, and there's more the merrier. Basically, if you're really interested, please come and look at what we're doing at the university and talk to us and engage. So I'll just go through the set of slides that's here, and anybody has questions, please type them in and ask, and certainly I'll try and answer anything that folks put forward. So, energy is fundamental to all of human life and life systems and the planet. And, when it comes to nearly everything we do, when you think of all of the manufactured products we have in our lives and, achieving transport and other things, energy is just so fundamental, and we rely on it for nearly everything. I mean, a world without energy to power, even a light bulb, so that we can stay up at night and read a book. I mean, you still need energy in whatever form it is, whether a candle, it's a conversion of energy from wax combustion into light and a bit of heat, and so on, all the way to a light bulb. You need all of that sort of thing. And, and I think, some of the stuff I'll present here is a bit introductory, but it's kind of fundamental to the idea of what is energy and the use of energy. So, fossil fuels, so these are petroleum-based energy sources, so like oil, gas, coal, and so they're based on hydrocarbons. So the idea of, you combust hydrocarbons, you get heat. Heat we can turn into dry fluids, and dry fluids we can turn into power, and that sort of thing. And so really in that sense, the energy stored in chemical energy, in the hydrocarbon bonds, the hydrogen, the carbon that's in that material. Second one is renewables, so that's a replenishable energy source, so solar, geothermal, wind, and so on, hydropower, wave power, and these are ones where basically the system replenishes the energy. So there's, consumption of stuff to build those systems, but the thing is you're getting energy that's replenished readily through the natural system. So for instance, solar, the sun is shining, you harvest it to get power. And the last one is non-renewable, so let's say nuclear power, so in a way an alternative to the other two that you have there. So when you think about energy systems, there's kind of a whole sequence of steps, and so we often think about the idea of manufacturing, and we think about the idea that if I'm going to produce, let's say, a cell phone, you're going to invest a set of energy and materials to build a cell phone. But we often don't think about the idea of manufacturing energy, right? It's something that folks don't think about, but that's what energy systems, that's what we do. So when you're an oil company or a solar company, it's about harvesting what you have to get greater amounts of energy out. And so what you have here in this slide is you see here basically we need energy to construct the energy generating system. And of course that will have some emissions and impacts, pollution or whatever it is that comes out of that impacts the environment. You will then have the realization of that energy generating system. So that's going to be, let's say, some sort of system ready to go and ready to be deployed. And then you'll have the energy production from the system, and you will have what we call a useful life of that energy generating system, which may be years, could be months, it could be a long time. And of course you'll have emissions and other impacts, and other impacts include land, water, and so on. And then at the end of the life of that system, you will then abandon it, and the hope is that you will then basically return things to what they were before. So you will then basically have to put in energy to do that, and you will have emissions. But you can see a whole kind of the life of an energy generating process here in this. And as an example, for instance, if you were to say, let's say, an oil production energy system. So in Alberta, we have a lot of oil reservoirs. And if you want to get oil out of the ground, well, you're going to require a certain amount of energy to construct the wells, put them in the ground, drill them and so on, complete them, and then connect them to a facility where you will gather the produced oil. And that has a certain amount of emissions and so on. You will then have your constructed oil processing facility with the wells and all that other stuff. And then what will happen is then you will harvest for some time, so the gray area in the middle, where you have the productive life of that reservoir, which will give you that oil in the form, the energy in the form of crude oil out of it. And of course, during that, you may create emissions while you're doing that kind of process, and then you'll abandon that, and you'll have to take energy to basically abandon the wells, clean up the facility, remove it, return it back to its state prior to all of that activity with consequent emissions. And you can imagine that for then, let's say, beyond, let's go to the next slide here, an oil refining. So now you've got that crude oil, so you've got that energy. You invested some sort of energy in to get the oil out, maybe in the form of electricity for pumps and so on, and you got the energy out as chemical energy. And so you can now imagine for oil refining the same kind of things. You will need energy to construct the facilities, the pipelines, rail distribution systems with impact, and then you'll have that ready. You will then have a conversion of chemical energy in the form of crude oil to now fuels and that sort of thing. So gasoline, jet fuel, diesel, and so on. And so then that will be operating for some sort of useful life, and then you will abandon it and return it all back to its original state with emissions to do all of that. So when you start thinking about these kinds of systems, the idea of clean energy, you have to wonder what that is, because all systems produce some sort of emission no matter what. And even if you were to start looking at, solar. So solar, well, here, yeah, on constructing the solar panels and transmission lines, all of that stuff, the cement and the materials that you might use in a solar panel, whatever they are, you construct it, you will have its useful life. Now, during the useful life of solar power array, it may be that the amount of emissions you have per unit energy generated is going to be quite small relative to other ones, but still the entire system on constructing it, operating it, and then dismantling it basically has impact on environment and so on. So you start to wonder about, well, how do you move to a system where you don't have impact? How do we have clean energy systems? Is there such a thing as a clean energy system? And
where does your research focus? Is it in this process, now that you've laid it out so nicely for us? Is it sort of beginning, middle, end?
Well, there's aspects of it which are at the beginning. So in terms of the reservoir side, we want to lower the emissions intensity per unit oil produced. Let's say now that oil is on surface, now you have a store of chemical energy. It's now about, well, how do you best use that energy. So how can we optimize it? The alternative is to look at how we can go one step prior to that and extract better forms of energy from these systems. So I'll talk about that in a minute. So, but all aspects, you know, when you think about the research at the University of Calgary, in terms of energy, we are attacking nearly all aspects of these systems with respect to, you know, the materials used to construct energy generating systems, the actual application of the energy generating system, and then also the cumulative effect of the system itself on the environment through its life, and then essentially how do you remove that in a clean manner to return the world back to something that it was before. So it's kind of funny because you know, we always think about and these are kind of my thoughts on energy, and maybe some folks would disagree with this, but you know, to me, energy is like a transactional system, you know, in a way, just like any material flow or even cash flow. In that, you know, what you're going to do is you're going to have a certain amount of energy that's invested into the system, and the hope is you get more energy out. So let's just say you put 1 gigajoule. A gigajoule is simply a unit of energy. You put 1 gigajoule of energy into it. You hope you get, let's say, you know, 10 units out. That's what you'd want. And in doing this transaction, you're basically now supplying this produced energy for other purposes, right? And so in doing that, you're, you know, it's a transaction on energy. Now, the cost of that is that, you know, in some systems you will have these greenhouse gas emissions. You know, you may have impact to land. So, for instance, a hydropower facility, you know, you store water that affects lands behind the dam, where you're now putting water there. Or wind, where you're affecting the land, where now you may impact birds and other things. So the thing is, all of these energy systems, they have impact. And, you know, the hope is that X units of energy go in and you get greater than X out. Very simple. But the funny thing is that it's a transactional system that may not be about energy production, because another way to look at this, which I think, given a world where we value commercial outcomes, right, and all that, it may be that you have a system where, you know, you have a certain amount of units of energy invested, and maybe you don't produce at the end of where the end use of that energy is really used. It may be that, in fact, that's less energy than you actually put in through the entire cycle of that energy generating process. But the thing is, the transaction is it generates value. And so it can generate value in the sense of, you know, basically money. So that's one thing, or products or services or other. So the thing is that, you know, an energy process hopefully is energy producing, but in some systems it doesn't really have to be, in that if it basically returns value that you can use for other things, then in itself it's a system that is healthy in that sense. Now, of course, we want, as a planet with climate change concerns and so on, and simply the attitude of being cleaner than yesterday, right? You know, we certainly want to reduce those impacts. So the greenhouse gas emissions and land impacts, water impacts, sea impacts, and so on. So, you know, but this is, to me, energy systems all about transactions. It's about swapping material and swapping energy in terms of its forms. It's about efficiency, and also within this world, it's about economics and environment.
And interestingly, we have a question about fossil fuels and how long it's going to take for us to stop using fossil fuels in Canada. And so is the answer related to the transactional nature of energy?
Well, I think that, I mean, it's a really hard question to answer, and in the sense that there are certain, you know, so fossil fuels have multiple transactions, in the sense that fossil fuels, so let's say oil, gas, coal, you know, for instance, let's just say oils. Well, oils can be used to build not just fuels, but products. So you can build, you know, asphalt comes from oil. Asphaltene-rich products come from oil. Gas can be converted into plastics. So the thing is, yeah, in terms of fossil fuels, it could be that we see for electricity generation, we might see some sort of transition there. But will that end the fossil fuel business? I don't think so. I think that there's still a need for those hydrocarbon molecules. So I think that there's multiple aspects to the question of, when we think fuels, well, maybe, but I'll show some data that may question that in a second. But the thing is with respect to the use of petroleum planet-wide, I suspect we will be using that for quite some time. It's hard to say, for instance, if someone was to say, well, in 2030, will oil and gas be done? I would say no. I think because the thing is we need it for more than just energy. Mm-hmm. It's a petrochemical feedstock which powers a lot of the products we buy in our lives. And certainly with plastic reduction and so on, and single-use plastics and other things like that, certainly there's a way to become more efficient on material use, but it's still a foundational element of what we do today in our lives, is using these products. So,
great.
Okay. So let's go to this. This is an interesting table here. So this is Energy Matters. This is Global Energy Demand. And what I want to make the point here about is, so on the first column, what you see basically energy vectors. So you have coal, oil, gas, nuclear, hydro, biomass, and you have other renewables, right? And you have a total amount of use in the second, or demand within the second column. You can see the growth rate there. So certainly what you're seeing here is that there's been no decline in any of these energy vectors. So energy demand on the planet is growing. That's certainly there. But what you see here is, look at the last two columns. It's very interesting, because if you were to look at the hydrocarbon bit of this, the fossil fuel part of it, what you see here is, you see in the year 2000 that 80% of the energy is coal, oil, and gas. And if you were to look there, nuclear is 7%. And then 13% is hydro, biomass, and other renewables. Other renewables include solar, wind, and so on. And then you go, let's say, 18 years into the future. So, yes, last year, so 2018. And what you see here is that you see for coal, oil, and gas, the mix stayed at 80%. So, there's a lot in the media and other places about the idea of energy transition, that renewables are taking over fossil fuels, right? But let's just look at data. And what you see here is, 80% fossil fuel versus 80% in 2000. So no change there. So that's not transitioning anywhere. Now, within the fossil fuels, there's certainly a transition where you're seeing now one of the biggest transitions with respect to energy in the fossil fuel arena is shale gas. So you certainly see a shift from coal to gas, in terms of the within, but it's 80% of the total mix. And then you see in nuclear, it's gone from 7 to 5%. And then what you see here in terms of renewables, it's 15%. So the energy transition, what you're seeing in the data, is really quite interesting. It's not a transition from fossil fuel to renewable. It's from nuclear to renewable, right? And so this is, I think that a lot of folks talk about, the idea of the end of fossil fuels as energy. But the thing is, the data is not suggesting that, and despite we see growth in renewables, we're seeing growth in the other ones too. And so the thing is, my hope is always, and personally my belief and hope is that we get to cleaner energy sources. But this is what we see in terms of the data out there.
I don't know where this lies in your research, but there's a question about the coal reserves that Alberta has. Taking a look at could they be used to produce the energy that we need to capture CO2 directly and then sequester it? Where do you see a role for coal anywhere in the future? Well,
it's interesting. We're endowed with quite a bit of coal, and yes, if you purely combust it and you then let's say generate steam to turn steam turbines to basically create electricity and so on, it emits a lot of CO2 per gigajoule produced, right? And it's the dirtiest form of power, and that's why you see a huge transition to natural gas for power versus coal. But the thing is, you start to wonder about it. If you were to instead admit up front that what you generate from coal, let's say you produce 1 unit of energy, and you were to admit right up front, I'm going to take 50% of the energy, and I'm going to now have only half the output from such a plant, but I'm going to take a huge fraction of the energy and put it into carbon conversion. I'm going to take that CO2 and I'm going to convert it into something else. Maybe there's a kind of an admission that, okay, we will not generate the amount of power that we generate from, let's say, a ton of coal when we start integrating what we can do with the CO2 as a product. And you start to think about, well, should we be putting more research into that? I think so, because it's a massive resource. I think the thing is I have to admit, if we have zero emitting fossil fuel sources of energy, in my view, that is a wonderful way to use that resource. Rather than, I love the idea of going clean, but these are still energy resources, just like if you have wind, or if you have solar. They're all energy resources, and if we can convert coal to be zero carbon emitting. So you could do carbon sequestration underground, and that is one route already being used by some folks. But the thing is there's costs and uncertainty there, but it is a route. And another route would be to to admit we're going to only produce a fraction of energy and then use that fraction towards converting carbon dioxide into other products.
Thank you.
But let's look at another aspect of this. So you start thinking about energy and electricity, So energy, when you start thinking of that, involves more than just electricity, because energy can be the fuel that goes into an internal combustion engine or the hydrogen that goes into a fuel cell. And then you look at electricity. Now here you might argue, well, there could be a bit of a transition in energy as well going on. So on this column here, you see coal, oil, gas, and so on. And you have the 2018 values of energy in terawatt hours that was generated. This is globally from International Energy Agency. And you see the growth rate, and you see a decline there in oil being used for electricity generation. So that's interesting to observe. But then look at the values from 2000 to 2018. So 65% of electricity came from fossil fuel in 2000, 64% in 2018. Nuclear, 17% from nuclear down to 10%. And then you do see a change here in renewables, where you had 18% in 2000, now up to 27%. But where did the big transition occur? Renewables are displacing nuclear.
Does that answer the next question then? Will 4th or 5th generation micronuclear plants, like the 30 megawatt brand, will that replace fuel carbon energy sources or fossil fuel carbon energy sources?
I think nuclear is something that should be explored quite a lot more. And the thing is there's a public, I think that many folks, when they hear nuclear, they think fear. But in terms of energy generation, we should be exploring it quite a lot more. Because, they don't produce CO2. Now, of course, they have a different waste, nuclear waste, which has other issues. But, there are ways to deal with that. So the thing is we certainly should be opening up more to nuclear and considering it as an option, especially these smaller units that are modular and they are safe and could be quite flexible in their application going forward. But again, it's interesting how the energy mix works. So you're not seeing a transition like we always hear in so many places. This idea of energy transition, and Bob Skinner, if you're listening, he is always telling me about this. But the thing is what you see is you wonder, with the data that is out there, where is this transition of fossil fuel to renewables? Because the data doesn't seem to support that. And I would love if people could correct me if I'm wrong on this and send me the data that proves otherwise. But fossil fuels, in terms of power with respect to energy total, is basically growing too, as is new renewables, and as a consequence, you're not seeing this energy transition, which I keep hearing people talk about. And
what will it take to get us to a future where renewables are a higher percentage of our energy generation?
Well, I think it has to be cost effective. I think that, a lot of folks, they love the idea of cleaner energy, but the fundamental thing is cost. So, but you're now seeing where costs for renewables are now really quite low. And I think you're going to see certainly a surge over the next while as, with these low electricity prices from solar and others, you will certainly see that change happening. And perhaps over the next, in the electricity world, you will see that transition happening and accelerating as we go forward. But, it's interesting that, still, the idea of fossil fuels within the idea of energy, I would love to see it, the CO2 impact intensity go down, but we need fossil fuels, that's really not the thing, petroleum, for other things other than energy. So it's not just about energy. So if you look at Canada, one thing that we should always reflect on in Canada, and I apologize if you can't see this text so well, but right here is Canada. So this is basically the percent electricity production from renewables in 2018. And what you see here is there's Canada, 66% of our power is from renewables, so hydro, right, and emerging wind and emerging solar and other things. But, Canada does quite well with respect to power generation. And, I think the one thing that is kind of strange to me is when you see, and you hear about such adversity to, what we do in Canada with respect to material production, so bitumen production, which some of it, much of it goes into fuels and into materials. But you look at Canada as a whole, we're doing very well with respect to renewables and power across this nation. So, and we're only doing better as we transition into natural gas-based power and so on, away from coal.
I see somebody here is interested in your bitumen pellets.
Oh, yeah.
So it's a little bit of a transition away from renewables. But
yes.
One of the things you're doing to make the transport of energy is, per se, a little bit safer. Can you tell us a little bit more about that research and how long it'll take for that to perhaps hit the market as a commercial product?
I'll be getting to that in about 5 minutes.
Okay.
Yeah, so I'll zip through some of this. So basically, in terms of clean energy, what I'm really getting at here is that there's no real clean energy systems. But if we were to look at useful life of an energy generating process, certainly there are less impactful energy systems out there. And the one I really want to get to is this idea that it's the hydrogen story. And then we'll get to the pellet story. But the hydrogen story, really what's wonderful about the idea of hydrogen generation is that as a fuel, if you can power the energy generating system with the produced hydrogen, it produces no emissions. And if at end use of the hydrogen you produce no CO2 emissions, it's a perfectly clean fuel all the way from generation all the way to end use. And so the thing is, in my mind, this is something that we should be paying more attention to. And, when you start thinking about where Canada is at with respect to hydrogen, you might wonder, well, do we have a lot of hydrogen? Well, we do, and it's in our massive oil sands and heavy oil resources. So when you look at Alberta and Saskatchewan, we have massive resources of oil and gas, and world leading in terms of the volumes and in terms of oil sands. And the key thing about these things is right now when we produce from these systems, these are very viscous oils. So think about peanut butter. That's what these things feel like. If you took peanut butter, put it in the fridge, that's what that oil feels like in the underground. And it's really quite viscous. You can't move it easily. So what we do is to move it, we inject steam into the reservoir. It warms up that oil. The viscosity drops so it looks more like water. And then we can flow it out of the reservoir. But the consequence on producing steam is basically burning natural gas. We put CO2 into the atmosphere. And certainly industry, when you start looking at the data, over the last 20 years, on average, you're looking at a reduction of, 25% in terms of the amount of CO2 emitted per unit of oil produced. They've done a good job in getting better, and you forecast that going forward. It's getting cleaner every day as they move forward with respect to what they're doing in producing this incredibly challenging resource to produce. in terms of chemical energy and so on. But the thing is the focus of all of this has been about oil production, hydrocarbon production. But the thing is, when you start looking at this, hydrocarbon is hydrogen and it's carbon. And so, when you look at an oil sands reservoir and you start thinking about the hydrogen value inside of that resource, there's hydrogen in the oil, there's also hydrogen in the water. And so the thing is, now the water is as valuable in some ways as the oil in these systems. The oil becomes the fuel, which enables the temperatures and the conditions, which then lead to basically gasification reactions, which then leads to hydrogen production, enables water-gas shift reaction, which produces even more hydrogen, and as a consequence of that, you will have now this hydrogen within the reservoir, which, if you put in certain materials in the reservoir, you can exclusively extract from the reservoir. So this is one aspect of the research that we've been doing over the last few years, and it's gotten very exciting as an alternative to producing oil from the reservoir. It's now about species production, producing a molecule from a reservoir.
What are the commercial applications for hydrogen?
Oh, so if you were hydrogen is used in many processes, for instance, ammonia production, which is, a massive chemical on this planet, methanol production. We use it for. It's also a fuel that can be used to produce power from, if you simply burn it to drive a steam turbine, or if you were to put it into a fuel cell and produce power by that method. It's an incredibly valuable material, and in fact, in Alberta, where do we use a lot of hydrogen? It's upgrading heavy oil. So basically, you take bitumen or heavy oil, and you put it through an upgrader, and part of that, you're adding hydrogen to those molecules so as to create a lighter oil. So we use a lot of hydrogen there as well. Hydrogen as a feedstock material for products, incredibly valuable. As a fuel, also incredibly valuable, especially because on use, it produces no CO2. So it's a beautiful fuel in that sense. So so here what we have is we're thinking about the idea that came to us a few years ago was, instead of produce oil, can we go to species production and produce only hydrogen from the reservoir? And then we also thought, well, the key here is that if we can produce enough hydrogen to power the entire energy generating system over its useful life, then both the extraction system is now carbon free, and then the end use of hydrogen at its wherever it's used. If it's used in a car to power a car, if it's used to produce electricity, none of it produces CO2. So that was the idea behind it. And there's a set of reactions, and if folks are really interested in those reactions and what happens in the underground, I'll put some resources online for them so they can look at those reactions in detail.
There's a question here about hydrogen in the atmosphere.
Oh, okay.
Could there be harm to the atmosphere if we emit hydrogen into the?
Not as a global warming gas.
Okay,
I mean, so in terms of hydrogen is fairly reactive, so it would be consumed fairly quickly. But the other side of it is, I think that. The systems, just like we try to minimize leaks, you try and design systems where hydrogen is captured and is not emitted to atmosphere. There's a lot of, you start thinking about the Hindenburg. When we think about hydrogen, I always think of those images of the Hindenburg where, a hydrogen-filled dirigible was exploded because it was filled with hydrogen. But the thing is, we've progressed a lot since the Hindenburg, and we have fairly safe ways to store and transport hydrogen. There's hydrogen pipelines in the U.S. where they transport hydrogen. A lot of folks will talk to you about the idea of metal and metal issues. Certainly there are those issues, but you can certainly design around them. And if you look at, for instance, the Mirai, which is a car which is powered on hydrogen, these tanks for storing hydrogen, they're high pressure, but they're very safe. And, I would say that, when you think about the idea of sitting in your car on top of, let's say, 60 liters of gasoline, or piping methane into your house, these are systems which we consider fairly safe, right? Sure. And hydrogen, as for its transport and storage, has evolved immensely over the last many years and is now can be transported and stored quite safely. So yeah, hydrogen has impact, but the thing is, as a fuel, certainly it has less impact than if you were to burn, let's say, methane, which produces CO2, and so on. And if methane escapes to the atmosphere, it certainly has its greenhouse gas potential, warming potential as well. But the thing is, so we're looking at essentially how do we get hydrogen from oil and how do we get it out from the water? And so the set of reactions we take advantage of is we inject oxygen into the reservoir, we do partial combustion, so we do what's called in situ gasification of the reservoir, and as a consequence of that, we produce hydrogen. And from there, we produce only the hydrogen from the reservoir, and we ignore all the CO and CO2 that is created as well. And we keep that underground. So we wouldn't want to do this process in a shallow reservoir where there might be potential for those gases to go to surface. But for any ones that you would do, let's say, where you have steam and you would have a steam-based process which has a nice intact caprock on it, this kind of process would be perfect for that type of system, especially if you have a lot of water, because we want to get the hydrogen out of the water as well. There. So this is growth of global hydrogen, and what you can see here is there's an upwards trend. From 75 to now, you can see this beautiful upwards trend of hydrogen, and you can see that quite a bit is used for refining of oil, so that's hydrotreating of oil, ammonia production. It's used as pure hydrogen for other uses and so on, methanol production, DRI, so that's steel production and other things. So you certainly see growing hydrogen in nearly all of these areas. So there's a demand for hydrogen. And it turns out Alberta, with our hydrocarbon stores and the water that's in there, has immense hydrogen stores. I mean, we could become the world's largest hydrogen supplier if we really wanted to with our resources. And we get a lot of questions about the technology. So when we were doing the research, we got quite passionate about this idea of how can we retrofit our reservoir production technologies to produce energy in the form of hydrogen from oil sands reservoirs and heavy oil reservoirs. And of course we started to say, well, we need to prove this concept, but we found there was proof in previous pilots that were done in oil sands reservoirs. And so one was this Marguerite Lake pilot, which was a cyclic steam pilot, and it also injected oxygen. And out of that pilot, what they observed is 20% of the gas was hydrogen, during some of the operation. But the thing is, it wasn't really considered a success because they weren't after hydrogen, they were after oil. So then we decided, well, okay, that's as a process for oil, well, it has certain strengths and certain weaknesses, but we can tune that process. We can retro-design it. We can optimize it to now produce hydrogen. We don't want the oil. That's the fuel. That stays in the reservoir. We never want to see that at surface in this particular energy production process. So the idea was, how do we design that process so that we can get greater amounts of hydrogen? And we did a lot of work, simulation and other, where in the end we could get up to 40%. And if you could look in there, it's hard to see, sorry about the font, but you could get 40% of hydrogen, and we've even gone beyond that. And from these simulations, that led to a whole series of experiments and so on. So we designed processes where we gasify the reservoir, we produce hydrogen through our membranes exclusively to surface, and we power the whole system using the produced hydrogen. And we did a bunch of experiments, so I'll just go through that, and the simulations. And then we did our first field demo in 2018 to try and show this. So it shows this kind of the most, in my view, ideal. I love it being a professor in this, where we can take what we discover in our thoughts, our concepts, our simulations to a lab thing next to then a field demo, and we're going beyond, where we can see our stuff going from the lab or the concept to beyond us, to application.
On that note, looking at that particular resource, if you were to extract the oil versus extracting the hydrogen, what's the difference in cost to the environment?
Well, so oil, if you were to extract bitumen and you were to then, if you were to look on, it's about, let's just say about 8 gigajoules per meter cubed to get that oil out. And then you go and upgrade that oil. So now you've, there's a bit of energy and emissions to upgrade that oil. And you then take that synthetic crude oil and you refine it. There's a certain amount of energy invested now in that to convert it from, synthetic crude oil into, let's say, gasoline, and a certain amount of emissions that come out from that process. You then take that gasoline, you transport it to the gas station, and so there's a certain amount of energy input and emissions that come from that activity. And you then take that gasoline, put it into a car, and you then burn it in an internal combustion engine, which may get up to maybe 35% efficiency. You do the entire realization of energy and energy costs and emissions, and so on. You'd wonder if it's energy positive, going from the invested energy in getting the bitumen out, right? So the amount of natural gas you burn, so the gigajoules there, versus the gigajoules realized at end use for that gasoline. Of course, it makes other stuff, jet fuel and so on. But let's just use gasoline for now. So the thing is, the invested energy at the beginning in natural gas, all the way through that pathway to the end to make gasoline, it's likely you're putting more energy through the whole chain than what you're realizing in terms of turning a wheel in a car, right? The thing is, it makes money. That's why we do some of that, right? We supply energy, but it also is commercially successful to do that. Now, if you were to go, let's just say, to a system where you produce hydrogen, and I'm not advocating against that. It makes sense to me, that system. But the thing is, if you went from invested energy in terms of, let's say, oxygen compression, which is part of our process, and then you produce hydrogen, and you converted that hydrogen, let's say you put it in a tank and put it in a car. So there's a transportation issue there, and energy and CO2 emissions likely arising from that. It's a far simpler supply chain to then put that in a tank, which then goes into a fuel cell, produces power, so an electric motor, so you have quite a bit more efficiency there to turn a wheel, right? So you start to wonder about the idea of what is the best path for energy, but also within the context of making value, right? So making money. But the thing is if you were to then burn the hydrogen at site and produce power and export it, you'll have transmission losses and other issues there, which, so you'll have losses of efficiency. So these are things yet to be looked at.
Some trade-offs.
There are some trade-offs there.
Someone here is wondering if there's the possibility to actually produce them both out of the same source.
Absolutely, and I think that's probably the hybrid model where, in some ways you're taking advantage of producing hydrogen and oil at the same time. And in fact, you start looking at some of these SAGD facilities where, you've got near end of life steam-assisted gravity drainage operations. These are perfect for hydrogen production. They're nice and warm. They've got lots of steam in them. And, we want to do essentially steam reforming of the oil that's in there. So the thing is, this is the perfect thing. And if you have some over here producing oil, you have some over here producing hydrogen, this is a great mix, especially if that hydrogen becomes the hydrogen you use to upgrade your oil that you produce. Because your hydrogen right now is coming from steam methane reforming, which emits a huge amount of CO2. But in this process here, where you're exclusively producing hydrogen from the reservoir, there is no carbon oxides to atmosphere. It's a zero CO2 produced process. So even if the cost point was the same of this versus SMR, but you get zero CO2,
there's a benefit.
There's a benefit there. So
there are a few people just wondering who you're working with. Can you tell us who you're working with
so
on these kinds of research projects?
Yeah, on this slide right here, there's a little company that was formed called Proton. I'm sorry the thing is so small, but Proton. If you're interested, go to www.proton.energy, and you will find more details on this. But we've done simulations, did the lab demo, did the field demo. And what you're seeing here is a photograph of us in February of 2018 in Carrobert, so that's near Kindersley, Saskatchewan, conducting our pilot. And it was the coldest day of my life, I have to admit. It was minus 31. And but we had a lot of learnings we had to run into the shack every few minutes to get warm again. But Proton is the company that is advancing this in the field. And there's a bunch of stuff. I'm going to sort of skip through this because I see time running through. But basically, there was a bunch of lab work done and simulations that you're there. There's our lab equipment producing hydrogen. And then to prove that we could burn something, we proved that. Do not do this ever in a lab, even though we did it, because you don't want to set things on fire in your lab. But we showed it was hydrogen. We were very happy with that, and of course analyzed it. And we got the flux rates for the membranes and so on, which we could then use in our simulations to then look at commercial outcomes from this. We did our first field pilot, so that was in February 2018, and you can see there's the site, and there's the team. We're in there in February, very cold. There's Jackie, a research engineer, the co-inventor of this process, and we conducted this in the field, and we produced from a heavy oil reservoir 99.9% pure hydrogen. And everything that we saw from the production rates and flux rates through those membranes were the same as what we had seen in the lab, which we'd then, of course, they guided our commercial design of the process. So,
quick question.
Yeah.
Are there design and safety changes required to the process and the facilities in order to switch from oil production to hydrogen production?
Oh, I'm sure you'd have to. There are some changes with respect to, you've got an incredibly reactive gas, but everything you do, for instance, in steam methane reforming, as is done right now in an upgrader, you'd simply adopt those. So, that the safety issues of moving hydrogen within the plant are no challenge, no barrier to using this technology in the field. What I want to really highlight on this slide is really the fact that when you do the commercial design of this, for what we're looking at the Robert site in Saskatchewan, we're looking at 18 gigajoules out per gigajoule in. And this is taking into account the fact that we're powering all the equipment on the site from the produced hydrogen. So in some sense, this becomes a clean operation, producing no CO2. The compressors are basically being powered from hydrogen, so either to power to hydrogen, power then to the compressors from the hydrogen, and then the fuel that you're getting at the end, the hydrogen, on end use and consumption is producing no CO2 as well. So we get 18 times as much energy as we put in. And, and as a comparison, if you look at SAGD here, so for a steam oil ratio of 3, which is a fairly standard kind of number people are operating at. There's many that are below that, some above that. But essentially you're looking at the energy return is 7 gigajoules per gigajoule. And then if you were to go through that full chain I described all the way to the point where you have, let's say, the turning of a wheel, what you might find is that, in fact, it's not so efficient as you would hope, and so on. So it's something to think about.
Quick question about the transport of hydrogen through pipelines.
Oh, okay.
Do we need to do something different with our pipelines to protect them from corrosion and
Yeah, there is a material selection issue there, so that's to make sure that you don't have embrittlement and other issues with the metal. But again, these are very well, we have hydrogen transport pipelines in the U.S. We have hydrogen lines within our upgraders in steam methane reformers where we produce synthesis gas. Hydrogen is present, and so on. And you have hydrogen in methanol plants. We've solved these issues, and so this is not a barrier to the execution of this technology at all. It is something to think about within the plant design, but it is nothing that would prevent us from doing the process. Yeah. The only other thing here is, so we get that energy return, but the nice thing about the process, because we exclusively produce hydrogen from the reservoir, no carbon, no oil, no anything like that, at least in the realization we have here. So it's a zero carbon emission process when you use hydrogen to power everything. Now let's talk about the other side of hydrocarbon. So hydrocarbon, yeah, it's hydrogen. We talked about that, and an option for producing hydrogen from a reservoir. So that's an energy vector and a feedstock material for products. And so the other thing what we've done is we've focused on the carbon side of the hydrocarbon. And always I thought was at first was to try and upgrade the oil, try and make it better. But what we learned is that we could do degradation. And what we found, there was value in degradation. So you start looking at asphalt on this planet, and asphalt, which is the stuff you build your roads from, is priced usually $5 to $10 above West Texas Intermediate. It's a more expensive product than, in fact, pristine crude oil. And so you start thinking, well, if we degrade our oils to get those kinds of materials, in fact, we add value to them, right? And we started to think about that. And in the context of transport of oil products from Alberta, with pipeline constraints and these kinds of things and so on, we started to think about, well, what can we do to, build alternative modes? And there are a few other folks looking at these kinds of things, so Canapux and Melias Energy. And we have our format here. So what we do is we take heavy oil and bitumen, which you see here in this beaker pouring out very slowly, and we actually convert, or we could take vacuum resid as well, but we convert it into two products. One is a pellet, which you see right here, and we also get this distillate oil, which has an API roughly on average around 23 API. And the nice thing about this process is the way we designed it is that, so these oils have sulfur in them. But what we found is we could put a lot of the sulfur in the solid, put very little sulfur in the liquid, so we actually get a value-added oil out of this. And the way we designed the process at first was we were so focused on pellets, but we've had a lot of chatting with folks over the last year and a half, and they like this distillate oil product, which is pipelinable. You don't need to add diluent or anything to it. And the key is what we've now focused on, and we've now got the process to the point where we can take 1 barrel of bitumen and we can produce 50% of it as pellets and 50% of it as distillate. And so there's no chemicals, there's no hydrogen needed. This is very simple kind of process that we built out of a kind of manufacturing process, so it's not a traditional process engineering approach to this. And we built this process so that, in fact, it costs roughly about 80 cents per barrel to do this operation. So a fairly low intensity process with very low footprint. The units are very small, and we're moving those units out. We've got one being assembled right now to be tested in the field, so we're quite excited about this. But another project that started at the university, and about how do we do better than yesterday, and driven from a kind of a sense of exploration and with no fixed agenda, was first focused on let's upgrade oil, to the point we came to degrading oil, but really what this process is both an upgrader and a degrader. So we take bitumen, we degrade part of it into the solid pellet, so we upgrade part of it into this distillate oil product, and we're certainly moving things there. Now, if you were to look at the value creation from this, $25 per barrel raw bitumen, people have different numbers. Some will say lower, some will say a bit higher than that. But if you were to look at, and I've been very conservative in pricing this, $36 per barrel for asphalt, but we've seen prices up to $80 to $90 per barrel equivalent of asphalt out there. But the thing is if we put this number in and you get 50-50 split on solid and distillate product, what you find there, taking in another conservative price for distillate oil with lower sulfur, we're seeing a per barrel increase of $18 in value, which, for many people might say, well, that's not much, but if you're producing 1,000 barrels per day of this is an immense amount of value you're creating here in terms of the oil. The other side of it is diversifying the mix. So instead of just straight bitumen and heavy oil, we're producing now 2 value-added materials from this. Now, one thing is that comes out with respect to emissions and so on, is that I'm going to zip to here, is that when it comes to transporting the oil, we have to transport vacuum resid or heavy oil or bitumen in heated containers or in pipelines with diluent. And so with this, we can transport the solids cold. There is no requirement for heat. And so the thing is that we see a reduction of about 30% with respect to GHG emissions for transport. The other thing is because we don't need diluent for the distillate product. you've just removed that cost from the equation. And when you start thinking about the loading of diluent in pipelines and the pumping energy that's required to pump that total mixture down the pipeline versus if you just put our distillate in there with no diluent, you've got a GHG reduction with respect to the core product you're really trying to transport.
So a lot of your research is about taking the resources that we're using right now from the oil sands and other oil and gas sources, and not necessarily going to renewables. How do you respond to people with regard to questions about what if the fossil fuels run out?
Oh, I think given our amount that we have in Canada, I think it's quite unlikely that it'll run out. And I think that if anything, certainly there's going to be social pressures out there that will, and they're rightfully so, to lower the CO2 emissions impact of fossil fuel energy. And so it's not likely we will run out of fossil fuel. There's sufficient out there, and in Alberta and in Saskatchewan, there's a huge amount of gas within BC too. There's huge amounts of petroleum reserves out there and resource to access for these products.
So we don't need to actually. It's not an all or nothing scenario where we're all renewables in order to be cleaner and greener.
That's right.
You can do a mix of both, continuing to clean up the system and the processes that we have in place right now.
Exactly.
Through innovation.
Well, exactly. And I think the key is that, we shouldn't be saying no to fossil fuel. If fossil fuels or petroleum, it's a resource. And the thing is, if we can access it and get energy at zero carbon intensity, so no CO2 to atmosphere, would we say that's bad? I would say that's awesome. We're using a resource. It's like forestry. You're using a resource and then we regrow trees and so on, and we use the wood in many things. So the thing is, if we have the balance there where we replenish in that sense, or we make it clean, right? There's no need to replenish fossil fuel on this planet. The planet's doing it itself already and generating new petroleum through millions of years of processing in the underground. If we can do it cleanly, I don't see an issue with that. So if we can produce hydrogen or zero carbon oil from these systems, to me, that's the objective. Use the resource to produce energy to help our lives, help our health, education, feed the world, and so on. But the thing is, it's do it cleanly, and if we can use petroleum to do that, why not?
People are really curious about this bitumen pellet of yours.
Oh, okay.
When will they be able to use it and see it actually in use commercially?
Well, we're going to do a pilot in BC, which will be a road asphalt pilot. So the beautiful thing in building a pellet is that it's not combusted. And so as a consequence, it's taking bitumen and then the carbon is fixed in the product, right? So we're not combusting it. It simply goes on a road, it goes on a roof, or serves as a carbon feedstock for other things. So it could be a carbon feedstock, for instance, for carbon fiber or other things. So the thing is in that sense, it's quite valuable. But the thing is, what you're going to see in the next year, 2020, you will see our 200 barrel per day plant. I keep dancing around it. I should just say it.
People want a date.
Yeah, so
okay.
So you're going to see the 200 barrel per day plant, and you're going to see at least the 1,000 per day, 1 barrel per day plant coming up, and we will be also. You'll see the hydrogen pilot going forward in 2020, hopefully. The thing is, things are not so quick as you'd hope, but the thing is, that's the nature of research. As we discover and we do things, it does take time, but it's very, very exciting.
Well, thank you so much for sharing a couple of the amazing things that you're doing to find cleaner solutions using the same resource. I just want to thank everybody for watching. Slides and a recording will follow by email for everybody. The survey is coming up. Make sure you don't forget to fill that out. And make sure you look for other webinars and download ebooks. Things like that are available for you as resources. Watching videos of these University of Calgary scholars keeps you up to date on what's happening. Thank you so much, Dr. Gates, for your time.
Very welcome. It was a lot of fun.